Hey everyone! So in this video we're going to talk a little bit about correlation and how we can use this to measure the relationship between two numerical variables. So correlation has a very special relationship in statistics. It measures a certain type of linear relationship. We'll start with some example data to really motivate where this idea comes from, and we'll start with standardized test scores as being our example. So we've got 200 observations that were randomly sampled from a survey called the High School and Beyond survey. This is done every year by high school seniors. So students take a standardized test with 5 components: reading, writing, math, science, and social studies. Now, you're probably not that surprised to hear this, but performance on standardized tests is related from subject to subject. To measure how related it is, we might look to something called like correlation. So here is an example of the relationship between the reading scores and the writing scores for this group of students. Now, as the reading score increases, the writing score tends to increase as well. We definitely have a positive linear relationship or an upward trend in this data. Not only that, but the data looks to be fairly linear. You can imagine where a straight line drawn through this data might fall. So it would make sense to say that there is a linear relationship between reading and writing scores. In other words, reading and writing scores are correlated. So in statistics, the definition of the correlation is as follows. Correlation measures two things. It measures the strength and it measures the direction of a linear relationship between any two numerical variables. So we'll represent the correlation usually with a letter R. Some books will use uppercase R, some will use lowercase r. I tend to use lowercase r when possible just to avoid the confusion with the software program R. So R represents correlation for us. Correlation is what we'll call a bounded measure. So that means that there's a limit. Correlation has to take on any value between -1 and +1. Now, if we have a positive correlation, if R is greater than 0, we say that there's an upward linear trend in the data, whereas a negative correlation goes along with a downward linear trend. If our data is scattered, or if there's no clear pattern, kind of a cloud shape to it, if you will, then there's no correlation. Now, after a while, it becomes fairly easy to look at a data set and kind of estimate the correlations. So let's look at some examples of what different correlations might look like. Now, on the right side of these plots, you see negative correlations. As we go from sort of a low negative correlation of -0.5, you can still see the downward trend in the data, but the points are definitely scattered. -0.9 is a stronger linear relationship. The points are tighter or closer to the line. And then at -1, we have the perfect negative correlation. All of the points fall on exactly a straight line. On the left-hand side of the graph, same idea. Stronger correlations like 1 or 0.9 will have points that are very close or exactly on the line, whereas smaller correlations like 0.5 will have points that are still fairly scattered. However, we can clearly see what this linear relationship might look like. Now, correlation can be deceiving, and to illustrate this point, I want to show you a data set that's fairly famous in the statistics world. This data set is called Anscombe's Quartet. This data set was designed with a very specific purpose in mind. All 4 of the scatter plots that you see here had the exact same correlation, specifically a correlation of about 0.82. Now we see in the upper right sort of a good linear relationship. Points increase along a straight line. That trend is pretty clear. Plot 2 actually shows a curve. So this is not a linear trend, but there's still a fairly strong correlation. Plot 3 has an almost perfect linear trend except for one outlier up here. And that illustrates a really good point that outliers can dramatically affect correlation. They can make the correlation weaker if the outlier falls off of the trend, or they can make a correlation exist where there wasn't one before. So with this last plot, number 4, there really isn't a trend at all in these points, aside from the outlier. So correlation on its own can be kind of a deceiving measurement. Now, I want to show you an example from another data set. So this data set has a correlation that's very close to 0. Here, I'm using a function in R called core to calculate the correlation. This data set has 2 columns, an X column and a Y column. So the correlation between the X variable and the Y variable is negative 0.06, very close to 0. Now, we might think that this should have no linear relationship, and it doesn't, but it does have a different relationship. This is a data set called the Dino data set. So, even though there's no clear linear trend, there's definitely a pattern in this data. Certainly not a pattern that would occur in real life, but a pattern nonetheless. If we add a linear trend to it, it's a big, flat, fat line. There's not really much going on. So some takeaway points from correlation before we look at some examples of how to work with this. Strong correlations don't guarantee linear relationships. I always recommend to never take correlation alone. Plot your data, calculate the correlation, look at those together to see whether or not you do truly have a linear relationship, or whether it's just a spurious or a chance correlation. So let's talk about how to find correlation. When we're working with a lot of numerical variables, it can be really useful to calculate all of the correlations at the same time. We do this using what's called a correlation matrix. So the core function in R, COR for correlation, will calculate all of the correlations for every variable in a data set. However, we get an error when we first try to do this, and the error says this: X must be numeric. Here's why we're getting that error. There's variables in this data set that are categorical, that are not numerical values. Gender is certainly one, race, socioeconomic status, school type, type of program. So those are variables that we don't want to include in any discussion of correlation, because correlation measures the strength and direction of a linear relationship. So the variables must be numeric for this to work. So what do? Well, we can use a function called select to choose which numeric variables we want to use. So I'm going to select out the reading variable, the writing variable, the math variable, the science variable, and the social studies variable. And I'm going to save what results from this in the scores data set. So now the scores data set, if you will, just includes these 5 columns here on the right. Just includes reading, writing, math, science, social studies. All should be numeric. So now let's visualize these correlations in a correlation matrix and a correlation plot. I like to go straight to the plot, even though we can certainly look through the table of correlations. I'm a visual person and I like how this looks. The library in R that contains this function is called the core plot library. So we'll calculate a correlation between all of these scores, save it in a correlation matrix, and then I'm going to plot this correlation matrix. What I get is something like this. So this plot uses circles and shading to indicate what the correlation between 2 variables actually looks like. So on the diagonal, we have each of the variables correlated to themselves. These are perfect correlations, so correlations of 1, which should be expected. Reading scores should have a perfect linear relationship with reading scores. So looking at the other circles, the bigger the circle is, the bigger the magnitude of the correlation. So for example, it looks like there's a pretty strong correlation between reading scores and social studies scores. There's still a positive correlation because the circle is blue, but it's a little bit weaker between social studies scores and science scores. So that's how we might interpret this correlation plot. Now that's just one type of correlation plot that you can produce in R. Another example comes to us from the Performance Analytics library. So I can take this scores data set that I created, this only contains the numeric variables, pipe it into a function called chart.correlation, and produce something like this. Now this is a little bit different. There's a little bit more information, but it's not that sort of nice colorful plot. So it's a balance between whether you want a plot with a little information or a lot of information. So on the diagonal entries, we have histograms for each of these, along with a smooth curve or a density curve drawn over each histogram. So we can see what the distribution of reading scores looks like, what the distribution of writing scores looks like, what the distribution of math scores looks like, science and social studies. On the lower half of these plots, you get scatter plots. So this first one here, this is the scatter plot for reading and writing. Reading is going to be on the x-axis, writing is going to be on the y-axis. This next one below it in the third row, first column, is reading compared to math and so on. So we get scatter plots for each of these, which makes it really handy to look and see whether there truly is a linear relationship. On the upper half, we get correlations. So if you notice, the font size changes for these correlations. The bigger the correlation, the bigger the font. That makes those big correlations really pop out at you. These red asterisks are results from a hypothesis test of whether or not the correlation is equal to 0. The more stars you see, the stronger the evidence that there truly is a correlation here. So let's take a look at another data set. This data set comes from a study called the Health Evaluation and Linkage to Primary Care study. So this was a trial done with adult inpatients who were recruited from a detox unit. The idea was if we can link those patients to a primary care provider or a physician, then they might be more successful in their post-detox treatment. So we'd like to know what variables in this data set are strongly correlated. So this data set is pretty large in R. Let me go ahead and open R up and actually show you what is contained in this. So this data set is in the Mosaic Library data. Let me change my color of my font just so you can see this a little bit better. So we'll load the help RCT data. We'll spell it correctly. Remember, R is case sensitive. And we'll look through this data set. There's a lot here. If I go to any data set and want to learn more about it, I can write a question mark before the name of the data set, as long as it's a data set that's prepackaged in R, that is, and get some information. So here we have 453 observations on the following variables. We have the subject's age at baseline, so their age when the study was started, whether they've used substances post-detox, a depression score, hospitalization score, days since they've used substances, and so on. So we have lots of information about how this subject has behaved post-detox. So we'll select the numerical variables here. Those are age, depression score, days using substance, days since linkage to primary care, risk for drug use, E2B, this is a measure of consumption, I1, I2, we'll look at those shortly, total, MCS, PCS, PSSFR, sex risk, average drinks, and maximum drinks. So here's the correlation matrix. Right away, a couple things pop out. There are some areas of very strong correlations, here, 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 and here. A lot of the graph is really blank space. There's a lot of no correlations. So let's look at some of these. First, MCS and CESD. These are strong negative correlations. So MCS, this is a mental component score. So this is a measure of mental health. Lower scores are worse. CESD is a measure of depression. Higher scores indicate more depression. So high CESD should reasonably be linked to low mental component. So that makes sense. Average drinks and maximum drinks are linked as well. That makes sense. Last variables that are linked that are kind of interesting are I1 and I2. I1 is the average number of drinks consumed per day in the past 30 days. I2 is the maximum number of drinks. So again, two variables that should reasonably be correlated with each other. Now, one downside of the chart correlation approach is this. Once your data sets get too large, once there's a lot of numerical variables, this plot gets really difficult to interpret really quickly. So if you can, I would limit yourself to maybe 5 or 6 at the most. We still can see, though, there's some pretty strong linear relationships in this data. There's some very high correlations in this data. It's just a matter now of trying to pick out what those variables are. So the last variable or the last data set that I want to take a look at in this section is sleep in mammals. So this data set includes data for 39 mammals distributed over 13 orders, so 13 classes of species. We're looking at relationships between factors and sleeping. So we have the amount of time that the mammals spend sleeping, amount of time they spend sleeping but not dreaming, dreaming, total sleep, lifespan, and so on. So we'd like to know which variables are strongly correlated with sleep and the nature of the relationship. Again, we'll identify the numerical variables. I've already gone ahead and selected those numerical variables out and put them into a new data set called Mammals 2. When I go to create this correlation plot of the Mammals 2 dataset, here's a slightly different way to write the code using those tidyverse style pipes. Either way is completely fine, of course. You get something like this. There's a lot of question marks here. Those question marks are because we had missing data. There were observations that were blank, or NA. To avoid those, inside this core function, this is what's calculating the correlations, add an option that says use equals complete.obs. This says use only the complete observations. So there are strong positive correlations between body weight and brain weight, strong positive correlations between total sleep time and non-dreaming time, total sleep time and dreaming time as well, gestation and size of the animal, and then danger and predation. So animals that are in more danger are likely due to be in danger from predators. One last example with this data set. This is small enough that we can use that chart.correlation function as well. This also accepts tidyverse style notation, so piping a data set directly into it, by the way. As you can see, those very small correlations have a very small font size in the plot. We're letting those essentially disappear and trying to pick out the strong correlations. So these are some tools that you can use to look through numerical data sets to try to find linear relationships between variables. Have a good day.